Hello and welcome to the continuation of our lesson on plastic. We'll see the reinforcement here on the continuous edge. The top reinforcement here, M1, these are top bars M1. Look at the direction. The reinforcement is perpendicular to the continuous edge. And we also have top reinforcement M3 on this other continuous edge, while you have span reinforcement here, vertical and horizontal direction, which will be the main and distribution span reinforcement is M2 and M4. And we are given the value of each of these. M1, which is here, is 130 kilonewton meter per meter length. So we are given that per meter length. And M2 is 100 and M3 is 90 while M4 is 60. So we will have that in mind while we are solving the question. So let's go ahead to the solution. So this is the solution to tutorial question 2. This is the assumed real yield line pattern. To the yield line here, this is a yield line and this is a yield line, while this dotted line is just to divide this into shapes, rectangles and triangles. So this dotted line from E, they are not yield lines, they are just to divide this into shape. So you will notice the way this yield line is different from the yield line that we had in our exam tutorial question 1. This is because in this question, this side AD is unsupported. It does not have a support. So when you are assuming yield line, you do not assume that any portion will rotate about that axis. So in this yield line pattern, this plate A is rotating about side AB. This plate, this other big trapezoidal plate is rotating about BC, while this plate 5 is rotating about CD. There is nothing rotating about AD because AD is unsupported. There is no rotation at that point. So as usual, what are we to calculate from the question? we are to calculate the additional variable action that slab can carry. And for us to do that, the first thing we do, the best way is for us to calculate the design load. And from the design load, we can use this equation to calculate for that variable action. This is our normal equation for calculating design load, where 1.35 is a factor of safety for permanent action. 5.0 is a permanent action that we have been given, plus 1.5 is a variable factor of safety for variable action, while QK is the variable action that we actually want to calculate. So by doing this, we can now have that W is equal to 6.75 plus 1.5 QK. So once we are able to calculate W, which is our design load, we can come to this equation and calculate for QK, because QK is the additional variable action that we need, while the additional UDL to be determined. Okay, so we go ahead. First of all, we assume the unit displacement. This point EF will be a point of maximum displacement. So we assume a unit displacement of 1 at that point and go ahead to calculate our external load, our external work done. Now, if you look at this for external work, plate 1, plate 2, plate 4, plate 5 are triangles and are similar. So like we did in the first example, we are going to calculate one of it and then multiply by 4. So what do? We go for our n delta. Our n delta is usually their triangle, the area of the triangle, which is half base times height, multiply by W, which in this case we don't know. Then we multiply by the displacement. So our base here is 6 meter. Our height is 2 meter. So we can now say that the area half base times height is 2 over 2 times 6 over 2 multiplied by W, which is our UDL. And our displacement, like we said in tutorial question 1, because it is a triangle, we use our delta as 1 over 3. So that gives us 2W for each of those plates. Now for plate 3 is a rectangle. So we just go ahead and calculate the area, our n delta. Rectangle is half base times height. Is length times width. So what is the width? 3.5. What is the length? 6 multiplied by W. Because it is a rectangle, our delta is 1 over 2. So we had 10.5 W. Now to have our summation n delta, this plate 1 that we calculated was 2W, but because there are 4 of them, so we have 4 times this plus this. So our summation L delta gives us 18.5 W. You can notice that our summation N delta is given in terms of W, the design load, because that is what we intend to calculate. Now we go ahead to calculate the internal energy, which is where we should pay a little more attention. First of all, we want to calculate the Hawking moment. For us to calculate the Hawking moment, you can look at this. Let's go back to the diagram, to the question. For Hawking moment, you can notice in span AB, we have this top reinforcement, M1. What is the value of M1? 130 kilonewton meter per meter length. We have this one, M3, that is across the continuous HBC, and the value of what is 90. So having that in mind, let's go back to the question. That is why we wrote Hawking moment capacity across AB is 130 kilonewton meter per meter length, while Hawking moment capacity across BC is M3 is 90 kilonewton meter. Actually should be per meter. So having that in mind, we go ahead to calculate our Hawking moment. For Hawking moment AB, which goes here, remember Hawking moment or internal energy is calculated as ml theta. So ml theta, where in this case m is the moment, L, which is the length of the Hawking length of the span. The h is actually length of the Hawking heel line is actually this place, which is 6 meters. So we have 6 here. Then m is the moment, the capacity of the moment across the sub-Hawking side AB, which we have said is 130. And so our theta is actually, this is the place where we are doing this rotation, this Hawking moment. This is the point of maximum displacement, and the distance is what, 2 meters. So theta is 1 all over 2. So having done that, we calculate our Hawking moment AB. We now go for BC. BC is here. Our L in that case is 7.5. That is the length. Our M, remember the moment across that BC was 90. And our theta, this is the place we are calculating. And this is the place of maximum displacement. And that distance is 6. That is why we have our theta here as 1 over 6. And that calculates our Hawking moment. So we go ahead to calculate our sacking moment. Our sacking moment, also when we go to sacking moment, remember again from the question, let's go back to the question. You look at that the vertical reinforcement here, span reinforcement M4 was 60 kilonewton meter per meter, while the horizontal one M2 was 100 kilonewton meter per length. So having that in mind, if you go back to the question, that is why we write here sacking moment capacity. The horizontal one M2 is 100, the vertical one M4 is 60 kilonewton meter. So we can go ahead. Remember the sacking moment BE and CF, they are the same. So we calculate 1 and multiply by 2. So we go and say sacking moment is what? ML theta. And remember, when we have a horizontal, a diagonal sacking moment, we always calculate the vertical and the horizontal component. So this is what we are going to do. First of all, we are calculating the vertical component, which is here. For this vertical component, you can notice that the length is what? 6 meters. So we have here. And for the vertical component, what is the reinforcement that is resisting the vertical component? Take note of this very well. The reinforcement that is resisting the vertical component is actually the horizontal reinforcement, which is this one, M2. And the capacity is 100. That is why we have 100 here. For the vertical component of the heel line, this is the place of rotation, and this is the place of the heel line, and that distance is 2. That is why theta is 1 over 2. So this is the vertical component. We now go to the horizontal component plus. The horizontal component is actually this one, this place here, where our ML theta is such that the length L is actually 2. Now the M, let's look at when we are calculating this horizontal component, it is the vertical reinforcement that will resist that heel line, and the capacity of the vertical reinforcement is 60. So that is why we have 60 here. And when we are here, the vertical component, this is the place of maximum displacement, and that distance is 6 meters. That is why our theta is 1 over 6. So when we calculate that, we have 320 kilonewton meter. So from there we can go ahead and calculate our summation ML theta, which is this for Hawking moment. For Hawking, this component is for Hawking moment AB, this is for Hawking moment BC, and this is 2 times the sacking moment BE and FC. So that gives us the sum of internal energy. Remember this law that we virtual work law of virtual work, we say that the sum of external work done equals to sum of internal energy dissipated. Please always take note of this. So that means our 18.5 W equals to 1142.5. From there we can calculate our W, which is our design load, and our W in this case is 61.76. Now after calculating W, W is not actually what we are using for. W is a design load. What we are looking for is a variable action QK. So we go back to this equation. Remember this equation that W equals to 6.75 plus 1.5 QK. When we go back to this equation, we substitute the value of W, which is actually 61.76, and then calculate for QK. And our QK is now given as what? 3.67 kilonewton meter. And by that we have calculated the variable action that we need using the hairline pattern, the first. So the next thing we do is to assume another hairline pattern. So this is our second hairline pattern for that tutorial question 2. Is similar to the first one, it's just that this hairline actually meet with this other hairline. They all meet at this unsupported edge. So once we have this is a realistic hairline. You need to spend time and learn how to come up with realistic hairline pattern. So the solution, the first thing we do is to assume a unit displacement, and the point of maximum displacement here will be this point E. So we assume that at that point the displacement is 1. That is what we call by a unit displacement at point E. So we just go ahead and calculate our external work. We have plate 1, plate 2, plate 3, and by virtue of our dimensions, they are not the same. So we will need to calculate them separately. So we go ahead for plate 1. Our N delta is the area of this triangle multiplied by the W, which is a UDL, multiplied by delta. And the area of a triangle, as usual, is half base times height. So we have 4 times 6 over 2. This is W, the UDL. And then we have our delta, because it is a triangle, as 1 over 3. And that gives us 4W at that. So we go ahead for plate 2, we calculate the same thing, it gives us 7.5. For plate 3, we calculate, it gives us 3.5, and we go ahead and find sum of external work, summation N delta. So that will just give us this plus this plus this is for plate 1, plate 2, plate 3, and that gives us 15W. The next thing is to go and calculate the internal energy, and we are doing for Hawking moment and sacking moment. Remember, the Hawking moment is at this continuous edge AB and BC. That is where we have the Hawking moment. So we can go ahead for AB, ML delta. Remember, 6 is the length, and 130. Remember, the moment across Hawking lead line AB is 130. Then 1 over 4 is actually our theta. So that gives us this. We do the same for Hawking line BC. The length of there is 7.5. The real moment capacity, that is that reinforcement across BC, remember, is 90. And our theta is 1 over 6. So we calculate that. Then we go ahead and calculate the sacking line. Sacking line BC and CE. They are not the same, so we are going to calculate it separately. So just like we did in our line pattern 1, we calculate BE here. You remember we calculate for vertical component and for horizontal component, and we do the same for CE. We calculate for both vertical and horizontal component. So when we do that, we go ahead and find our summation ML theta, which is this plus this plus this. This is for Hawking moment AB, Hawking moment BC, and this is for the two sacking moments. So it gives us this. So remember, always remember this. Sum of external energy equals to sum of external work equals to sum of external energy. So that means that 15W equals to 703.9. And by doing that, we calculate our W to be 46.93. Having gotten this, we go ahead and go to this equation again and calculate for QK. In this case, our QK was 26.79 kilonewton per meter squared. So we go ahead. So what we will do is to repeat the same for one additional heel line pattern. And when we receive that, we also calculate for QK again. After that, we will compare the three value and select the lowest value of QK as the additional variable action. That is, we need. Remember to state your reason. The reason is that yield line